details, more we can do with distillation column, and which is also known as rigorous distillation column. So we'll discuss. Then we will go to the reactors. Then we'll move on to the reactors. So before I move on, if any student have any questions, any issues, kindly let me know. Very good, no issues. So I'll directly jump onto the DWC. I will share my screen. So I hope you're able to see my screen.
Yes, sir.
Yeah, thank you. So just click the new simulation, and I wanted to do the rigorous distillation column. In the simple distillation column, the simple distillation column, we can find out number of theoretical trays, actual trays, and reflux ratio, and the feed tray. At what tray we need to introduce the feed tray number, we can find out. And it also gives you condenser duty. That means how much heat needs to be removed in the condenser and how much heat needs to be supplied from the boiler, we can find out. So these are the things we can find out from the simple distillation column. From the simple distillation column, when you simulate the simple distillation column, you can find out these. So actually, if you have a simple binary system, it actually doesn't make any, it doesn't look any complicated. Or we just say I'm able to calculate easily by using hand. Why do we use this complex software? Actually, the software comes in handy because often you will not have a simple binary system. You will have a complex, like 4 to 5 components mixes. 4 to 5 components will be present in the field. Then you want to purify one. So sometimes we need to use multiple distillation columns. At that time, these calculations, these softwares comes in handy. So for example, crude, let's say we have the crude oil and it is going to the atmospheric distillation unit. It is very, very special. Like this is very, 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 like crude oil distillation is the, of all That's a little difficult and more wide application unit it is. So I will give information. So for example, in the crude oil, we have C2, that is ethane, and propane and butane, let's say n pentane. We have, let's say, four components. If you have to do a McCabe-Thiele method, or you know when you have these four components, it will be very tough. If you have to estimate the number of theoretical stages using the McCabe-Thiele method, it will be very difficult. It won't be so easy to find out. It is more easy for you to solve using the mass balance equations. It is more easy or more convenient to solve such problem using the mass balance equations or even the softwares. So for example, we will do, let's say ethane is 30% and propane is 20% and butane is 40% and the pentane is 15%, so 10%. Let's say this. If you have to do McCabe-Thiele method, it is very difficult. You have to do ethane, propane once, butane, pentane once. Like this, we have to do it. But if you do the software, that will be very quick. So, for example, we take this one, ethane, propane, butane, and pentane. So here I have selected all hydrocarbon components. So which of the property packages I should use? Hydrocarbon components, which property package it comes to your mind first? Come on, guys, please answer.
Sir, could you show the list once more?
You want me to show the slide, huh? Original one?
Sir, cow, cedar.
1 second. Yeah. So first I'll ask whether these are polar components or not. Somebody else apart from Warren, because he's answering most of the question. Somebody else. If no one answer, I will have to call the name. So if you answer, you will get marks. If you don't answer, I will call the names. I'm actually writing it. You won't believe me. You can see class responses. I don't want to open this file, but I'm writing every day who is responding, because my only aim is that you should participate. I want you to teach. I want you to learn. That is only my intention. There is no other intention, right? So I want your participation. And if you don't know, you say I don't know. So can you open a slide? I'm happy to do it. Just wanted interaction, not any other pressure or force to put you. So let's say this slide. These are hydrocarbons. Are these polar components or non-polar components? Ethane, propane,
Sir, non-polar.
non-polar. So who's actually answered?
Sir, it was me.
Okay. Yeah, so these are non-polar components. So this is polar and this is the non-polar. Non-polar. So these real components or pseudo-real components we have to understand. So these are the real components: ethane, propane, butane. So which one to be used? So this is the polar. So we go here. Now we have two options. So these are the real components. So which one we will use? What property packages should be used? What happened? Or someone answering? Which property package I can use? I can use either Ping Robinson or Lec4 or Lec4. These are the things I have to use it. So, of course, um, Clear also gives the prediction, but more simpler one or more easy one is Ping Robinson or Redlich-Kwong Sayove, SRK or Lec4. So any one we can select. Any one we can select. So Lec4, see this is Lec4 and Ping Robinson. So this is the Ping Robinson. And this is the SRK advanced and SRK. So anyone we can use it. Anyone we can use it. So I select Ping Robinson. Go next. So I finish it. So here I am doing the distillation of these hydrocarbons, right? What pressure should I operate? The distillation column should operate at what pressure? Distillation column pressure. This pressure matters. I can operate any pressure or pressure matters or only temperature matters because it's distillation. Come on, students, you want your input. So here, this is the components are there, and I wanted to know, or I wanted to pressure, what pressure I should operate. Can I operate at atmospheric pressure or not? Can I operate this distillation column at atmospheric pressure or not? That is the first question. Rakesh, can you give an idea? Can we operate at atmospheric pressure?
Yes, sir.
Yes. Okay. So what is ethane, propane, butane? Are they gaseous or liquid form at atmospheric pressure? Rakesh, these four components are the gases or liquids at atmospheric pressure. Let's say atmospheric temperature, room temperature.
So liquid.
Ethane is liquid. Ethane, propane. The gas cylinder we use in home, no? It contains predominantly what?
Yes.
Gaseous. So can we operate distillation column for a gaseous components? Distillation process? Distillation column is mainly meant for liquids or gases. Rakesh?
Yes, sir.
Yeah, distillation process used for separating liquids or separating gases.
The liquid.
Liquid. So can we operate atmospheric pressure? Can we operate this at atmospheric pressure?
Sir, I think yes.
No. So we cannot operate this at atmospheric pressure. So if these components are there as a pure components, we cannot definitely operate this at atmospheric pressure. Only these four components are there. If only these four components are there, definitely we cannot operate at atmospheric pressure. If you operate at atmospheric pressure and the normal temperature, if you want to operate at atmospheric pressure, these components has to be, the temperature has to be negative. So they have to be liquid state. They have to be liquid state. So atmospheric pressure, no. So we have to use high pressures. We have to use very high pressures. So I'll just taking this data from a research paper where they have actually did the simulation. This is the simulation. Here, ethane, propane, butane. I have just taken N-pentane. He has taken hexane also. So they're operating at 1654 kilopascals. 1654 kilopascals. So almost 1654 kilopascals. So this pressure we can operate. So we'll introduce the material stream. Temperature pressure. Temperature pressure we have given, and the compound amounts: ethane 30%, ethane, propane 20%. So 0.3, 0.2, and butane 0.4 and 0.1. Total 1 and accept it. Total 1 and accept it. So stream conditions. So 1654 kilopascals. 1654 kilopascal. So molar flow and moles I kept it same. I didn't change anything. So these are this one. Now we wanted to see, let's say we have this and we wanted to see how many theoretical trays required, how many actual trays required, how many trays required. All this information we will find out. All this information we will find out. Now, when you have four components, what is your target component of separation? We have to determine. In a distillation column, always we have to specify what is the light key and what is the heavy key. What is meant by light key, heavy key? Do you remember? Light key components. What is light key? What is heavy key? Anyone remember? Anyone remember what is light key and what is heavy key? Light component. In terms of boiling, something is light component, means lower boiling point. Heavy key refers to the higher boiling point. Light components refers to lower boiling points, and heavy key refers to the higher boiling points. So in distillation, another significance with this light key means components having boiling points lower than this will be there in the distillate. Will come from the top. Maybe that is easy to understand. Will come from top. Components having a higher key, components having boiling point higher than this will come from bottom. So if you have a single, let's say binary system, that will be easy. Light key component that is come from the top, heavy key come from the bottom. But we have multi-component system, then this specific terminology will be helpful for us to understand. Light key and heavy key. So if you select ethane as a light key, then only ethane will come from the top and rest of the three will come from the bottom. The distillation will be designed such that rest of the components will be come from the bottom. Suppose we define, if we say light key is ethane. That means I want to separate ethane from this. So what will happen from the top of the distillation column, from top, all ethane only will come. And from bottom, rest of the three components will come. Of course, some portion of these components will be there, but predominantly ethane will be there. Rest of the three components will come from the bottom stream. Will come from the bottom stream. I hope you're able to follow. When you have multi-component system, we have to define light key and heavy key, and the significance of that means this one. Suppose if you define, I'll just rewrite so that you may understand better. Suppose if you define light key as propane, from the top, ethane and propane will come predominantly. And from the bottom, rest of the two will come. Rest of the two components will come. So which is butane and pentane. Later on, if you want to do, so if you have multi-component system, if I want individual pure components, suppose ethane, I'll just copy paste this, ethane, let's say we have 4 components. If you have 4 components, if you wanted to make them individual pure ethane, pure propane, then we always need n-1 distillation columns. We need n-1 distillation columns. If you have multi-component system, let's say 4 components are there. If you want to purify all the components of 95% or higher, then we need n-1 distillation columns. So what it means? So let's say I define propane as light key. Then what I'll get from the top? So from these 4 components, after the first distillation, we'll get 2 from the top and 2 from the bottom. Now we have to use another distillation column to separate these two into we need another distillation column to separate ethane and into propane. Similarly, we need another distillation column to separate n-butane and pentane into individual components. So this way, 1 distillation column, second distillation column, third distillation column. Since we have 4 components, 4 minus 1, 3 distillation columns required to make them purified. So this is multi-component distillation. So let's see. This is the feed stream. This is the feed stream. Columns, shortcut column, or simple distillation column. So simple distillation, feed, distillate. We want to distillate, create a new stream of distillate, bottom stream of distillate, condenser duty, and reboiler duty. So we need to provide these streams. For distillation column, we need to provide these streams. So this is distillate, and this is bottom product. Distillate a top product, bottom product. So yeah, so here we need to define what is the light component. Let's say I define ethane is the light component, and I'll have to define propane as the heavy component. So whatever conditions you want. Let's say I wanted a light key mole fractions in the bottom, like ethane composition in the bottom is 0.01, and H key mole fraction, the distillation is 0.01. So we'll make it 0.05, and we'll make it 0.05 and enter. So it automatically gives you all the values. It gives you all the values. It calculates for the required specifications what you want. For the required specifications what you want, it gives you minimum reflux ratio, minimum number of stages, actual number of stages, and everything it will gives you. So you can see the distillate. In the distillate, if I click the distillate and the compound amounts ethane 0.95 and propane 0.05, and butane is very less, and pentane is very less. So you got the top product is 95% purity ethane came. From the top, you got the 99% ethane came. From the bottom product, you can see all the three components will be there. Ethane is 1%, propane, butane, and pentane. All the three came into this one. Now, if you wanted to purify, suppose if you wanted to purify these three, because it contains propane, butane, and n-pentane, we need to add additional distillation column. Like we can put another distillation column. So feed to this one will be the bottom product 1. So feed to this will be bottom product 1. And here we need to create distillate stream. Again, bottom stream, condensed duty, and reboiler duty we need to create. So here this is, let's say this is ethane rich. Ethane rich, that is majority is ethane. Then I wanted to make it as propane rich. Propane rich. So let's go to distillation column, define what is light key and heavy key. So here light key is propane and heavy key is butane, and let us make it 95% purity, and it calculates. So again, it will show you how many number of distillation, how many number of trace required, and you can see, click on the propane rich and you see the compound amounts, and the propane is almost 91% purity, almost 91% purity. So here in the bottom product, now we will have only two components. Ethane is very less, propane is very less, and n-butane and n-pentane are there, 78% and 20%. So we can add another distillation column to purify it. So this is another distillation column. A feed to this one will be stream 9, because we are connecting this one. Now we'll create distillate, bottom product, condenser duty, distillate duty, reboiler duty, and light key component is n-butane, and heavy key component is n-pentane, and just solve the flow sheet. And it gave you all the number of critical stages, condenser duty, reboiler duty, optimal feed stage. So this way, if you have a multi-component system, the software becomes much more handy. much more easy for us to do all the calculation. If you have to do by hand calculation, it is possible, but it takes longer time. It takes longer time. If you're interested, we can also see, we can write a program by ourselves to do all these calculations. So this is a way the multi-component distillation. And here we have 4 components in the feed. We have 4 components in the feed, so we need n minus 1, that is 4 minus 1, 3 distillation columns we need to use, and all the calculation becomes simple. And for every distillation column, the information what we get is what is the minimum reflux ratio, and what is the number of minimum number of stages, actual number of stages, optimal feed stage, at what stage we need to introduce the feed, and liquid percentage and vapor moles, and here the condensate duty and reboiler duty. All the information we can get it from the simple distillation shortcut column. I'm sure you have done this in a mass transfer, but just to solve one problem, it took a lot of time. Like we need to get thermodynamic data, vapor liquid equilibrium data, plot a graph, then find the Q line, all these things. But the software helps to run the background program that will help us to solve this in a very quick manner. You all understood? Do you have any questions?
So does the ordering of how we choose light key component, heavy key component have a big impact in the end? For example, in the first distillation column, if we choose ethane and instead of propane, we choose butane and then go forward with it.
Yes. Then what will happen? Suppose if I choose butane, then ethane propane will come here. Then instead of distillation column here, I had to put the distillation column here.
So how would you say which one is more optimal, this setup or the one with just the 3?
We have to do both, and we have to see how much net amount of energy, like we have the reboiler duty. So this is positive. We are removing the energy, and this we are supplying energy, and we have to calculate net energy demand and number of critical stages, what way it is coming. We have to do it. There is no simple straight rule that this only gives you. One thing we can say, if the boiling point difference is, let's say we have ethane, propane, butane, right? Okay. I don't remember the boiling point. Let's say the boiling point is 120 and this is 125, and let's say this is 140 and this is 145. If let's say these are the boiling points, assuming to be, then obviously it is easy to separate. It's good to separate these two first and these two first. So at that time, this is light key and this is heavy key. If you define that is better. That way we can then we'll have maybe less number of stages required. Suppose if the boiling point difference will be 120, 125, 130 and this 145, then obviously it is better to say N-butane is the light key and N-pentane is heavy key. So it depends upon the boiling points and net energy demand calculations. After calculating that one, if whatever gives the net energy demand is minimum, and whichever giving the minimum number of stages, that we prefer. You understood, or are you able to answer? Have you got
Yes,
your
sir.
answer?
Understood. Yes.
So this is about shortcut column. There is another call here, another option in this DWSIM or in this process simulation software is distillation column. Right now we're only getting this information. Only we are getting this information. But suppose we want to know what is the temperature. What is the temperature at each tray? Temperature at each tray we wanted to know. Let's say if you wanted to know what is the temperature at each tray and what is the vapor and liquid composition at each tray. If you wanted to know, we cannot get it from this simple distillation column. what are the vapor liquid composition in each tray, what is the temperature at each tray, and what is the pressure at each tray. And if you want to know that, yeah, we will not be able to use a simple distillation column. If you want to withdraw, if you wanted to, if you want to use multiple feeds, if you want to use multiple feed stream into distillation column, again we can't use simple distillation columns. If you want to use multiple feed streams, again we can't use simple distillation column. And if you want to do any side streams, if you want to withdraw side streams, we cannot, let's say, instead of taking only at the top, only at bottom, sometimes we also draw liquids from the side streams. So if you want to do that, we cannot use simple distillation column. If you wanted to use these four, there we have to use the rigorous distillation column. We have to use the DC option. This is also known as rigorous distillation column. You can see here rigorous model for simulation of distillation column. Rigorous distillation column. Rigorous distillation column. This helps you to get what is the temperature of each tray, what is the vapor and liquid composition in each tray, and if you want to do the side streams, and if you want to use multiple feed streams, we can use this one. Simple distillation column cannot be used. So, but in the rigorous distillation column, you need to give, it won't calculate number of stages. You need to give number of trace information, and feed tray location, and pressure at condenser and reboiler has to be given. Condenser and reboiler needs to be specified. If you want to use rigorous distillation column, sorry. Yeah, if you want to use rigorous distillation column, you need to provide number of trays, you need to give number of trays information, feed tray location. So from the simple distillation column, we can get approximately how many total trays required. Like we can add this one plus this one plus this one. That give you typically how many trays required. For example, for this, in the first tray, we need approximately 10. In the second tray, we need approximately 7, so 17. And here again 10. So if you want to use this, almost we need 27 distillation trays. Usually reduces and usually less than the total sum of these, but maximum of that number we can give. And suppose if we give less than that required one, desired separation still happen, but the diameter of the distillation column slightly increases. So that way, even if we decrease, it won't make any big effect on the distillation column design. So I will save this multi-component distillation column. I actually just wanted one hint. Do you guys allow to use the software, or do you guys want to write programs to do this one? I don't know why only few people are showing interest. What is the interest? You love programming? Then we can do programming. If you love to learn the software, we can learn the software. What makes you more interesting? At least give this int so that I can plan accordingly my lectures.
So software.
Okay. So if because out of 100 only 15 students are turning up, that somehow making me a little feel bad that yeah, am I missing or am I not catching the pulse of the students? That's where I'm a little bit worrying. If you guys wanted for programming, we can do full programming. I'm okay with that. But if you wanted to learn software and explore faster, that also we can do. So what makes you more interesting? And I'm happy to teach. So there is no problem from my side. Honestly, we are here to make you understand, make you learn the course better, make you become a bright chemical engineer. So that is only my simple motivation and concern. Even to ask questions in between. If people don't want to come up just because I will ask questions, then maybe we can stop it. But that won't help. Ultimately, that won't help. So just wanted to make you understand. That is only my interest, not no, nothing else, no other motivation. Yeah. So some of you are at least two of you respond software, so I'll proceed with software. Some people says that when I ask questions, one or two response, then I'll go based on those two responses. But if majority feeling discomfort or whatever, they can always give advice. We happy to take advice of students and mold ourselves to make you more interesting. That is the only thing. So we'll move on to this rigorous distillation column. So here I have taken actually this example from this paper. This is very old paper, and what is the I will upload it. The why I like this paper is they have given what is the different methods they use to find out this rigorous distillation column. A typical distillation column is split into individual stages. Like a typical distillation column has multiple stages. Now in the rigorous distillation column, we write mass balance and energy balance across each stage, and we will also write mass balance and energy balance for the overall distillation column. So suppose we have multiple feeds F1, F2, Fj, Fn minus 1, and here multiple side streams SL1, that is side stream liquid taken, vapor is taken as side stream, so SV2, so SV1. So this is the maximum possible chances they're keeping here. And we can give intermediate heat to the specific tray. So this much Q1 amount of heat is given to stage 1, Q2 amount of heat is given to stage 2, so Qj amount of given to stage. Like this for each stage, they have written what are the possible streams that can go inside, what are the possible streams that can come outside, and what are the energy streams that can go outside. Everything is given. So for this, we can write a mass balance. For this, we can write a mass balance. Probably I will, if I explain here, maybe it will better for you. So I'll just take a small distillation column. So this is, let's say this is the one, like typical distillation column. If it looks like this, I just want to find out. Where is this? The symbol I'm looking for. Yeah. So So this is the top of the distillation column, and fill. So these are the intermediate stages. So this is the bottom of distillation column. So, okay, at least I could get near distillation column. And we can have multiple feeds. We can have multiple feeds. We can have multiple feeds. There's a possibility. There's multiple feeds. Multiple streams can be taken from intermediate trace. Multiple streams can be taken. I will also tell you why we need to take multiple streams. So this is the side streams. These are the side streams. We can take side streams. These are the side streams. And this is the feed 1. Feed 1. And this is the feed 2. So we can have multiple feeds, right? So this is tray 1. Where is this? So this is the tray 1 of, sorry, I cannot. So this is tray 2, tray 3, tray 4, tray 5, tray 6. The bottom is 15, so I'm not writing here. So there are 15 trays. So our aim is, we wanted to know what is the temperature at each tray and how this affects if we take out some side streams and all those things. Now, this is one tray. Let's say this is one tray, tray 3. Tray 3. Let's say this is tray 3. From the tray 3, let's say we have feed, we are giving a feed at tray 3. Tray 3. What in the tray 3, what will happen? One feed stream is going into tray 3. I'm just only talking about only one tray here. So there's only one tray. I'm just filling it, only tray 3. So the feed liquid is going in. And here, let's say one side stream is also coming out. That is from outside the distillation column. Within the distillation column, what will happen? What will happen? Liquid from drop tray will come, right? Liquid from the drown comer will come, and liquid will leave from the tray 3. Similarly, vapor come from the bottom, the boiler goes to the tray 3, and the vapor will leave the tray 3. So the vapor entering on tray 3 will be, let's say, V3. Amount of liquid coming out from tray 3 is L3. Similarly, amount of vapor leaving the tray 3 is V2. Amount of liquid entering the tray 3 is L2. And we have F moles of feed. F moles of feed is going into the F1 moles of the feed is going into the tray 3. And let's say we are taking out liquid product S1 side stream. S1 amount of liquid is taken from the tray. And now we can do the overall mass balance for this tray. Anyone suggest me what is the overall mass balance for this? Overall mole balance, not say mass balance. Let's say overall mole balance. Any suggestion from student side, or anyone can tell me what is the mole balance? Please. Overall mole balance. Moles input equal to moles output, right?
Yes,
Yeah.
sir.
Yeah. So input equal to output. This is the mole balance. Input equal to output. So F underscore 1 plus that is feed. L2 is feed. L2 is feed and V3 is feed equal to inputs. Outputs are V2 is output and L3 is output and S underscore 1 is output. So that is this one. And we can do the component balance. How we do in component balance, what will come? Mole fractions will come. F1 into X is the mole fraction, XF, and L2 is the XL2, XL2 or X2, whatever X2. And V3 is the Y3 because vapor is denotes with Y, Y3. Similarly, V2 is vapor, so denotes with Y2, Y underscore 2. L3 is L3 and denotes with X underscore 3. And S1 is again liquid, so X underscore S1. So this is the overall balance. Now we can do energy balance also. F1 into enthalpy 1, L2 into enthalpy of liquid stream 2, V3 into enthalpy of vapor stream 3. That way we can write energy balance. Now we can see exactly every time. This is Vj1 into Yij1, Lj1 to Xj1 minus this mole fraction. So we can write material balance equations. Now at each tray assuming to be at equilibrium, assuming each tray at equilibrium, we can write the mole, we can write the, using vapor liquid equilibrium data, we can write the y equal to kx, y equal to kx form, y equal to kx form. So this is the equilibrium relationships. Then we have the sum of the mole fractions equal to 1. That we know. Sum of the vapor mole fractions, sum of the liquid mole fractions equal to 1. And this is the energy balance equation. This is the energy balance equation. So they are trying to solve these 5 equations. They were trying to solve in the rigorous distillation column. They will solve these 5 equations that will give you enthalpy of each tray. From enthalpy you can calculate vapor temperature and liquid temperature, and you know Yij, Xij. From that we know the mole fractions of each component, and L and S1 side stream 1 we can know side stream flow rates, and we can play with feed flow rate. So I will upload this paper and they've given, see this is the diagram which I showed. I just did the diagram for one tray and they have done diagram for all the trays. Then this is the simple algorithm and you can easily understand. So that's the rigorous, that's this, I guess, a little bit simple explanation of the rigorous distillation column. Now let's see in the DWC. So I'll just take 2 minutes break to use washroom and again we'll start. And please stay online. Yeah, I'm back. So I just wanted to, from this research paper, based on the information they have given, I wanted to simulate this rigorous distillation column. So yesterday I was looking for some information. Luckily I got this paper, so I'm sharing with you. So I'll close this, and I open new simulation. New simulation. So here in this research paper, so they did ethane, propane, butane, pentane, and hexane. So I will take these components: ethane, propane, butane, pentane, and hexane. So I have selected. So now any one of you can tell me what property package I will use. Here I have selected ethane, propane, butane, pentane, and hexane. What property package I will use?
Ping Robinson.
Yeah, just now we used, right. So Ping Robinson, then finish it. Oh, I should have selected system of units. So I will just select system of units according to this one. They have given kilopascals, then kilomole per hour, temperature in Kelvin, and pressure in kilopascal. So I will not use SI. I will use any one custom unit system. Let's see. C5 or C4, yeah, C4 kilopascal and Kelvin. Just to make things little easy for me, I'm just selecting, and molar flow rate, kilomole per hour, and anything else I'm missing? Kilopascals, kilomole per hour, Kelvin. Yeah, so that's kilopascals, Kelvin, and kilomole per hour. So I have selected C4 just to, for the convenience sake. So feed stream. So this is the feed stream going inside. Now I want to see what temperature the feed stream at 349.78. There are two feeds. This is, you can see, two feeds. Feed 1 and feed 2 are there. In the example 1, feeds, there are two feeds, feed 1 and feed 2. First of all, I'm creating the feed 1. Then I'll create the feed 2. Probably if I open with so there are, see, this is the feeds. There are two feeds. So two feed streams. So this is feed 1. This is the feed 1 and feed 2. So first I'll create feed 1 stream. So feed 1 stream, and temperature is 349.78 Kelvin, 348.7 Kelvin, 78. That's okay. So pressure is 2067.94, 2067.94 kilopascals, which is there. Now we know temperature, pressure, and stage number. This feed is entering at stage number of 6, and this feed is entering at a stage number of 9. That we will have to define later. So we will enter the moles. Instead of mole fractions, they are given kilomole per hour. So we will enter this in terms of moles. So this is 1.136, 1.136, 6.364, 6.364, 8.636, 8.636, 2.273, 2.273, 0.227, 0.227, 227. So after that, I just say accept it. When I accept, it will convert to the mole fractions automatically, and we will have to change the total moles. We will have to change the total moles. That is 18.636. 18.636. So this is the total moles. So this is the feed 1. I have defined feed 1. Feed stream 1. Now I will need to create another feed stream, that is material stream. So this is the feed 2. Feed 2. So the feeds 2 stream is at 383.11. 383.11. 383.11. And pressure is 1895.63. 1895.63. This pressure. So 0.227 is the first component. So again, I'll go back and mole flows. Did I put it mole flows only? I will check. Yeah, this is mole flows. And here ethane is 0.227, 2.727, 2.727, 8.182, 8.182, 13.636, 0.045, 0.045. Here I kept it as mole flows. Okay. So the total is 37.1597. 37.1597. 37.1597 mole. So this way I got the feed stream and compounds. Then I got the feed 2 streams and the compounds. So I have 2 feed streams. Let's see what else is given. So the feed 1 is entering at 6 tray and feed 2 entering at tray 9. Now top pressure, see top pressure is this much and reflex drum pressure is this much, reboiler pressure is this much. So they given the reboiler pressure, top pressure and reflex drum pressure. Now always we will have the reboiler pressure is higher than the top pressure because the fluid has to move, the vapor has to move from bottom to top. It will only move when we have some pressure gradient. It will move when we have the pressure gradient. So that way always we have some reboiler pressure. Reboiler pressure will be slightly higher than the top pressure. Now stages, the total number of stages is 16, and this is the partial condenser. Partial condenser means the vapors coming out from the distillation column partially condensed. It's not fully converted to liquid. So you will have some vapor, some liquid. So you will have vapor product and we have the liquid product. We have the vapor product and we have the liquid product. Unfortunately, in the DWSIM, this vapor stream from the partial condenser is not there. this option is not there. So partial condenser can be selected, but how much vapor we are taking, how much liquid we are taking, all those things we are not able to specify very well. We are not able to specify very well. The options are there, but that's not giving a proper specification. Option is not given, proper results also not coming. So we can operate a full reflex. I will also show you both partial reflex and full reflex. So here we have the vapor top product and liquid top product, both is known. And here this is the bottom product. In the bottom there are three bottom products. One is liquid side stream 1 at stage 3, vapor side stream 1 at stage 13, and reflex ratio is given as 7.5. And heat extraction, they're taking out the heat, this much amount of heat they're taking out at stage 3. And also DWSIM doesn't have this heat removal, intermediate heat removal and intermediate heat supply. This is not there, so we cannot do that one. So we cannot do this one, heat removal calculation in the DWSIM. So with whatever we have, let us do. So columns, since we want to do the rigorous distillation column, we'll go with this distillation column, not the shortcut distillation column. So here, this is the rigorous distillation column. Rigorous distillation column. So number of stages. How many number of stages we need to enter? Here it is given that number of stages are 16. So this is the number of stages 16. So I am just entering 16. Number of stages is 16. How many iterations? As I showed you, this is basically we need to solve the equation simultaneously. So it is iterative procedure. So 100 iterations by default value. And here there are two methods are there: Wang-Henke bubble point method and simultaneous correction method. So in the Wang-Henke bubble point method, what we assume, what this in this method is that all the liquid streams leaving the trace are at the bubble point condition, and that way we can get some approximate temperatures value from that. But rest of the procedure, the main procedure is that we need to solve these equations. We need to solve these equations: mass balance equation, and equilibrium relationships, and energy balance equation. We have to solve these 5 equations. There are some assumptions, slight difference between assumption between bubble point method and this simultaneous correction method. So often they use bubble point method if the boiling point difference is narrower. If the boiling point difference between the components are narrower, they will use bubble point method. If the boiling point difference is significant, then other method is more preferred. Naphtali Sandholm simultaneous correction method. So that is first general tab. We will navigate through each tab, specification tab. In the specification tab, we need to specify condenser and we need to specify reboiler. We need to condenser and we have to specify reboiler. So condenser top pressure. We need to specify condenser top pressure. And you can see here it is given top pressure 1654.23. Condenser top pressure 1654.23. So here actually we will not have option to select the units. That is why I have gone to that custom units. Previously, we can select units, then automatically converts. But in this rigorous distillation column, it doesn't actually gives you option to change the units. It fixes. That's why I have to do this custom unit system to make my life easy here. So top pressure is here, and condenser type total, partial, and full reflex. So I'll go for the total condenser, then we will go for partial later, and pressure drop is 0. Reflex ratio, and here reflex ratio is given as, this is the reflex ratio. Reflex ratio is given as 7.5. looks too messy. Yeah, reflex ratio is given as 7.5, so I'll enter here 7.5. Enter value, then click enter. Unless you click enter, that won't take actually. If you're doing subcooling, that is beyond the condensation, then we need to enter here. So there is no subcooling mentioned here, so we don't need to enter anything. Then we'll go to the reboiler. We'll go to the reboiler. Where is the pressure drop? Heat load. It's not come. Let's be having information of temperature. Reboiler pressure is given. This should be there. Product mass flow, compound mole fraction, compound fraction. Okay, I don't know. I'll check. So stages. So here I need to create a stream for the top product, and I need to create a stream for the bottom product, and I need to create energy stream from the condenser, and I need to create a stream for the reboiler. So go back to the distillation column, specification, then stages. Stages. If you want to define, like by default it takes as efficiency 1, but if you want to define like 0.9%, 90% efficiency or lower, we can set here. Then connections. So we have 2 feed streams, and here always the connection ports, there's a maximum of 10 ports are available. Now since we are taking the 16 distillation columns, roughly we can take the port nearby that one, that is 1.6 times the feed one. So the feed tray is, this is 6 one. So 6 into 1.6, roughly into 1.6. So roughly, what I'm doing, 6 divided by 1.6. So around port 3, I will select port 3 as feed 1. And this is 9, again 9 by 1.6. Here we have taken 16 and 16 stages, and it only 10 ports available. For the rough port, I am just calculating that one. So at the port 5, I am giving the feed 2. I am giving the feed 2. Now, products distillate. Which stream is coming from the distillate? Stream 4. See, this is the stream 4, which is coming the distillate. And now I'm connecting the bottom stream. See, connected now. Bottom stream is 5. It's connected. Now, if you want to take overhead vapors, like in the partial condenser, we can specify overhead vapors here. But if it is total condenser, we don't need to specify here. Now, duties. So condenser duty. So this is, let's say, this is energy stream. This is C duty, condenser duty. That is amount of energy required or amount of energy removed from this condenser goes into the C duty, and amount of energy needs to be supplied to the reboiler goes to this R duty. So we connect this connections, the duties, C duty and R duty stream. Now side streams, if you want to withdraw any side streams, we can define here. So side stream 1, so I will have one side stream, let's say intermediate side stream. So one side stream is 8. The stream number 8 is taken as one side stream. And here these are the feeds, these are the products, these are the duties, and these are the side streams. Now we need to specify at what tray the feed 1 is going on. So at tray 3, at stage 3, the feed 1 is going on. 3, right, or 6? Sorry, stage 6. At the stage 6, the feed 1 is going on. At stage 9, the feed 2 is going on. The distillate is coming out as the stream 4 from the condenser. The bottom product stream 5 is coming out, the reboiler, and the side stream, one side stream is taken at stage 3. One side stream is taken at stage 3. Now, this is the stage. Now, side specifications. How much amount of liquid you want to withdraw? Because we are saying that side stream we are taking out, and how much amount of liquid we want to take it out. We can see that amount of liquid we want to take out is 1.364. 1.364. I just entered this number. Then we wanted to estimate the temperature, liquid flows, vapor flows, and composition. So this is the initial guess values. It is taking the initial guess values. So that's why this tab is there. And I guess specifications, stages, and results. Once you enter all this thing, then you click on the solve flow sheet. As soon as you click on the solve flow sheet, it does the calculations. It does all the calculations. How much amount of heat is removed and how much amount of energy is supplied from the reboiler. We can rotate this. So reboiler, this much amount of heat needs to be given. And here view temperature, pressure. So this is the pressure at each stage, and let's say the temperature at each stage. The condensate temperature, the liquid which is leaving the top one at this temperature. So these are the temperature profile across this one, and these are the flow rates. These are the liquid flow rates, vapor flow rates across the stages, component flows. So these are the at each stage. Let's say stage 1, what is the vapor composition ethane and vapor composition propane, vapor composition butane, pentane, hexane. Similarly, liquid, the stream leaving the tray, what is the composition? Every detail, every single detail we can get it from the again now with the fraction, mole fraction wise, these are the details. So in the rigorous distillation column, we are able to see temperatures, we are able to see the flow rates, we are able to see the individual components and individual mole fractions. So that is the beauty with this rigorous distillation column. So here, this is what I mentioned. We are able to get what temperature at each tray, what is the vapor liquid composition each tray, and side stream. Now, if you want to see side stream composition, just click on the side stream 8 and see what is the composition of the side stream. And you can see the composition of top stream. You can see the composition of bottom stream. You can add multiple side streams. You can add multiple feeds. You can take out liquid side stream, vapor side stream, and of course we don't have an option to give heat input or heat output. But what is the reason for taking side streams? Can anyone give me an answer? Why? What is the application? Any application where we need side streams? If you have ever known to this crude distillation, let me take out. So if you see this crude distillation image, the crude oil goes into distillation unit. Okay, they will take out different side products from the distillation unit. So they will take out the stream having the temperatures lower than 85 degrees Fahrenheit will predominantly contain butane and light products, which goes for the LPG. The streams having range between 85 to 185 is taken as a gasoline blending component. The stream having the, as you observe, the temperature varies from bottom to top. The temperature varies from the bottom to top. You can see the temperature varies from the top to bottom. The temperature varies 372, 367, all these temperatures. Similarly, liquids temperatures, this varies. Vapors and liquid temperature varies. Now, when here we have the higher boiling point, here we have the lower boiling point components, and temperature varies across the distillation column. So at this side stream, at this tray, the liquid component will be having this boiling point range, and that will be taken as a gasoline. And here they taken as a naphtha, and here we taken as kerosene, and here we taken as a diesel. So in the crude distillation unit, there are multiple side streams taken out based on the boiling point range as a side products. That's why it is important to know what is the side stream and what is the composition, what is the temperature range. If you have to do manual calculations, we have the, let's say, 5-6 side streams, it will be very difficult. It is possible, but it's very, very difficult. So that's why we're using a program, and here the software, they already run the program for us, and we're just clicking the options so that it saves a lot of time for us. Any questions, students? I hope you are learning something important.
So could you select the feed to stream one? I think I got that wrong.
Sorry?
Feed to stream composition.
Are you able to see, or should I zoom it?
So I can see it.
Do you got it right?
Yes, sir. Thank you.
Yeah. Students, please understand, this helps. A lot of calculations can be done in a very, very less time. If you have to do by yourself, it definitely possible. And you see, we need to write a code. This is the algorithm, how the algorithm flows. Overall mass balance, the individual component balance, the bowl point calculation, then energy balance calculation. So just solving these 6 set of equations in the background and giving us the values. Just similar to this, we have an absorption column. Whatever we are doing here, we can do same with absorption column. So I will leave it to you for you to practice the absorption column. Columns, absorption column or extraction column, exactly similar to the whatever I have explained so far. So please practice this absorption column. So that way I have explained shortcut column, distillation column, exactly similar features. So please practice absorption column. And whatever we are doing, shortcut column, distillation column, absorption column, you can do ChemSep column. This is similar, but this is externally connected. While installing, you might have got ChemSep. See, while installing, you would have got this tab ChemSep. This is external one, chem separation. So it goes to there, and you need to just give same details whatever we have given here. This is an external additional software from the original DWSIM. So we can do same. We can do same, and results will be similar. The results will be similar. I hope you are able to understand. Other students, do you have any questions? Are you able to understand? Rakesh, are you able to understand?
Yes, sir.
Okay. Others? Okay. So if you're understanding, that is good. And if you practice once, you will be understand. If you listen and leave it, then you will forget very fast. Just like we practice just by watching YouTube and we forget very fast. Same thing will happen here also. So I'm trying to give more details, more explanations so that you will understand wider applications. So that's about rigorous multi-component. Rigorous distillation column. So now we talked about streams, the separators, then we mix spreaders, columns. So now we have reactors and exchanges. Okay. Now we have reactors and exchanges. So I'll move on to the reactors because that is another important one to understand or to learn. Before I move on to reactors, in your thermodynamics course, did they teach chemical reaction equilibrium? If the professors taught you the chemical reaction equilibrium chapter. In thermodynamics course, are the professors taught you chemical reaction equilibrium chapter? I've not asked questions, just to know whether it has been taught to you or not.
So could you repeat?
In the thermodynamics course, professors taught you chemical reaction equilibrium.
Yes, sir.
Okay. So it's this one totally based on that. So I don't know whether this book or some other book followed you, but I will just show you how that chemical reaction equilibrium calculations looks like. Any book is same, whatever book you refer, but the calculations will not change. I could get this, I could download easily online, so I'm just showing here. I just want to go to the chapters. Phase equilibrium 562. It's chemical reaction equilibrium. So this is extent of reaction. The extent of reaction, right? I don't know whether you heard extent of reaction, expressing the mole fractions based on the extent of reaction. And this is the formula to find out the composition based on the extent of reaction. Hope you done some of the problems on extent of reaction. No? Extent of
Yes,
reaction.
sir.
Okay, very nice. So go on to this. So whatever you have learned in this chemical reaction equilibria, you can do all these calculations very fast using the software. Like I just want to give an example. So here, hope you're able to read these letters. Yeah, so you see this is production of ethylene from ethane. This is an example problem I am taking just to show you. So ethane is decomposed to ethylene and hydrogen. Just give me 1 minute. I'll just make a phone call. So actually, I had to inform one, so I suddenly had to call. So this decomposition of ethylene to ethane to ethylene and hydrogen. Now, if you add this temperature and at this pressure, what will be the equilibrium composition? Because equilibrium composition refers to the maximum composition. From the composition, we can get the maximum possible conversion that can happen. So if you have to solve, we have to express this in terms of extent of reaction. Then we need to calculate the equilibrium constant from the delta G. Then you will have to relate. Then you have to find out all this, and from this extent of reaction again we do the composition. Again we'll get the composition. So since you already this, I think this was taught in thermodynamics. Again, I don't want to teach. It might be boring for you. So there are three options. One is K can be estimated as constant, and K can be a function of temperature that can be taken as 298, and the K can be calculated as higher than 298 temperature at reaction temperature. So there are the three conditions is applicable. So it depends upon the reaction to reaction. We need to select a right condition. So we will see how to solve this problem in using this software. So I'm just closing this as it's not required. DWSim, yeah. I'll go to DWSim, close it, save, open a new one. Now I need to enter ethylene, ethane, and hydrogen. Ethane, ethylene, ethylene, and hydrogen. Hydrogen. So I need to select it. So I've selected three components, and if you want to know what are the components I've selected, just remove everything from search option. Then you will see what all you have selected. If you delete whatever information entered in the search option, then whatever you have selected that will pop up in the top. So ethylene, ethane, and hydrogen is selected. Then go to next. Which property package we will use here? Apart from Warren, anyone can answer me. Which property package I should use here? That is the important basic step in DWC. If you make a mistake there, everything goes mistake. No. So what property package? That means you have not yet started practicing DWC. So maybe it's a good time to conduct some tests in the next week. Oh, no. Now we have a lot of competition, so we will not do any tests now. You will be in trouble. So maybe after 2 weeks we will think about it. Yeah, what property package? These are these hydrocarbons? Ethane, ethylene, and hydrogen. Come on, students.
Yes, sir.
Yes. So for hydrocarbons, what property packages we prefer? For non-polar, hydrocarbons are non-polar and their real components. Non-polar real components, what we prefer? Peng-Robinson, Lee-Kessler, and what else? Not able to remember. Huh? I know you guys are very sharp, but I don't know why. So Peng-Robinson or SRK or Lee-Kessler. Lee-Kessler. So since we used Peng-Robinson last time, so I'll just use SRK Advanced. Finish it. So material stream that going inside. So in the feed here, in the feed, the temperature is 1000 degrees centigrade and pressure is 1 bar. Pressure is 1 bar. The temperature is 1000 degrees centigrade. So I should say 1000. It wants a degree centigrade, so select. Then automatically calculates into Kelvin. Pressure 1 bar. So I'll check 1 and select bar. So it takes 1 bar equal to 10,005 pascals. Molar flows doesn't matter. Now compounds. Now we will see in the input contains only ethane. Ethylene and propane are 0. Propane are 0. So this is only pure component 1, 0, and 0, and accept. So the feed contains only ethane. Ethylene and hydrogen are 0. So that's what we define the feed. Feed to the reactor. Feed to the reactor. So now we wanted to know we wanted to calculate the equilibrium composition. We wanted to calculate the equilibrium composition. So since we want doing the reactions, we have to go to the reactor tab. We have basically 4 types of reactors: conversion reactor, CSTR, PFR, equilibrium reactor, Gibbs reactor, both are same. Equilibrium reactor, Gibbs reactor, both are same. So you can use any one for the equilibrium calculation. So I will use equilibrium reactor. Equilibrium reactor. So go to the equilibrium reactor. So is in red, that means we haven't given the equilibrium reactor. Equilibrium reactor. So we haven't given the required conditions. So inlet stream is feed, outlet stream is one outlet stream for the vapors, one outlet stream for the liquids, if at all liquid products are there, but we need to specify, and one energy stream that gives the sufficient energy input. Now, this reactor does not know Now, what are the parameters? Still it is red color. Although we given correct, that means still some more missing. Now, what is the reaction set? So this doesn't know what reaction is happening inside. So we need to enter the reactions. So to give the input of reaction, just select this gearbox, gear type of the symbol settings. Settings. In the third row, first row, second row, and third row, click on the tab, click on this one called settings. In the settings, we have compounds and thermodynamic property packages, then reaction. So here we need to define the chemical reaction. We can do the multiple reactions, single reactions, we can do it. So just like we have the 4 types of reactors, we have the conversion, equilibrium, kinetic, and heterogeneous catalytic reaction. These are the 4 different types of reactions are possible. Right now we're looking for the equilibrium. Later on I'll explain conversion and kinetic one. So equilibrium reaction. So this is decomposition of probably we'll say ethane. So here all the 3 components we select will come. Ethane, we wanted to include in the reaction. So just click on include. Ethylene, we wanted to include in the reaction. And hydrogen, we want to include the reaction. So when you have multiple reactions, some components will participate, some components will not participate. So whatever components participate in the reaction, we will click include. Whatever components will not participate, we will click doesn't include. So basis is ethane, and the stoichiometric coefficients for reactants minus sign, for products plus sign. So here the reaction is C2H6. This is the reaction. C2H6 gives C2H4 plus hydrogen. So reactant is ethane and products are ethylene and hydrogen. So this is -1. Ethane is -1. That is reactant. Ethylene is product +1 and hydrogen is product, so +1. Now, once you enter the stoichiometric coefficients, we should always say the stoichiometry, it balances, it will come as 1. Okay. If it get balanced, it will come okay. It doesn't balance, it will show you some number. So C2H6 gives C2H4 plus hydrogen. So now whether it's liquid phase reaction or gas phase reaction, we have to know. So in this case, this is the gas phase reaction. So we will have to select vapor. We'll have to select the vapor. So we can take any basis, whether if a gas it has a basis or molar concentration, it could be anything. So just take vigacity. So this temperature is maximum minimum. It varies case to case because it is totally depends upon the convergence. So by default we took 2000. If doesn't give, then we keep changing. We'll try to change the value until you get the proper answer. Now, one thing I wanted to see here. Yeah. So here they're taken delta H of reaction is constant. And you can see delta G of reaction is 100,990. 100,990. And you can cross check whether that will, you can see 100,360, close to that value. So you can see that from the Gibbs free energy value, it calculates by default. So you can take it as constant or you can calculate here. So plus OK. So once you define the reaction, you can close this settings option. Then you can select default set. Right? Now, at what conditions you want to do adiabatic conditions? It is giving wrong. So, want to do the isothermal conditions because we wanted to have the same temperature. Because we wanted to have the same temperature at inlet temperature. We wanted to estimate, right? We want to estimate the equilibrium conversion at this temperature and pressure. So, we have to take isothermal condition. Because we already given the feed temperature as 1000 degrees centigrade and 1 atmosphere pressure. So we have to do the isothermal conditions. Once you click on isothermal conditions, flow sheet got solved. The flow sheet got successfully executed. Now we want to see the results. What is the conversion and what is the extent of reaction? We can see the composition. So this is the composition of vapors. Ethylene is 0.49, hydrogen is 0.49, and ethane is 0.01. And you can see this is the moles, 0.91, 0.91, 0.9. These are the moles, and here is given composition, mole fractions it is given. So let's go to here, moles of ethane, ethylene, hydrogen. So the moles is 0.09 and 0.91 is 0.91. So we wanted to calculate total moles is sum of all these three. So mole fraction is this divided by this. Then I can repeat the same calculation. Oh. Come on. Dollars. So this is the mole fraction. So ethane is 0.047. Somewhat wrong. Ethylene is 0.49, 0.47, and this is 0.49, 0.47. Slight variation. Can anyone tell me why slight variation? Because here when you define it, it is taken as 100, 360. But here in this book, they haven't taken as 100,990. Because of the small variation, you will see the small variation in the composition. Here in the book, they have taken delta G reaction as 100,990. The software took it as 100,360. Because of that difference, this small variation has come. So you can take ln K as function of temperature, and there is if you go further for ammonia reaction, and if for a function of temperature, we need to solve this big equation. So we can directly give this as input. And we can do this calculation. So whatever equilibrium composition calculations you have done in your chemical reaction equilibria, just by few clicks and few definitions, you will be able to find out. What is the need of this equilibrium composition? What is the need of this equilibrium? Here we have shown for this reaction, what is the equilibrium composition at this temperature, at this pressure. I hope you all remember in the CPT, I don't know if they have that. In the CPT, I have explained you the need of this equilibrium data. Where is this? So 19. I explained you. So this is the thermodynamic data, equilibrium data. So this is N2 plus 3 has to give ammonia. So ammonia content in y-axis and temperature in x-axis, different pressure. So if you get at different pressures, different temperatures from the composition, that is ammonia mole fractions, we can get this thermodynamic data. And industrial plants, at what temperature, at what pressure we should operate, and whole design of that reactor, one of the important information we need from this thermodynamic data. I hope you remember the ammonia content with different pressure, different temperature. So right now we have only calculated, we can do for ammonia hydrogen also. So next example is that one only. So we can do, I will let you to practice at 500 degrees centigrade 1 bar pressure. See 500 degrees and 1 bar pressure. This is 550 bar pressure. At 1 bar pressure, you will get almost nil conversion. But as pressure increases, you will get this one. In Aspen, this whole diagram, we can give the range of pressures, range of temperatures, everything we can give in and we can do it. But in DWSM, we don't have that facilities. When I teach Aspen, I will show you how to get this graph in a few clicks. So that's all about equilibrium reactor. Next class, we will see conversion reactor, CSTR and plug flow reactor, and we'll move on. So next week, we will try to talk about reactors. Okay, students, thank you for your kind attention.
Thank you, sir.
Hope you are able to learn something. Whatever you're learning in your masters for reaction engineering, thermodynamics, all the calculations we are trying to do with this software in a quick and fast way. All these calculations will be useful if you work in chemical process plant. Okay, if you got any questions, you can ask me. Otherwise, thank you. Have a great day.
Thank you, sir.
Thank you. So, no questions. I'll take attendance, download attendance, and end it. Okay, so no questions. If you got any questions, you can always message me. Assuming that none of you have questions, I'm just ending the meeting and thank you.